So today we are going to talk about function notation. This is going to be a full lesson about function notation to give you a reminder of how to use this and why it is important. So the first thing I want to address is what it actually means. What is the core idea? So we have a function that can be denoted by any letter. Most of the time you'll see f, and then you'll see x here. This is the input. So what this means is that it's the function f evaluated at x. And we can kind of think of this as like a machine. So when we plug in something, x in this case, into a function, no matter what it is, we are going to receive an output. So the function f evaluated at x, that result is y. Right? And that's why f of x equals y. What it is not is a multiplication problem. This is not f times x. So what I want to do is work through some different examples with you to kind of show you how this applies. Let's go ahead and substitute a number into a function. So let's start off with a quadratic function like this. If we are given a function f and we have f of x equals negative x squared minus 2x plus 12, and we are asked to find f of 8. What that means is that we are evaluating the function f at x equals 8, which means that everywhere that there is an x in our function, we are going to replace it with an 8. And then we are going to follow the rules of order of operations, and we are going to evaluate this function. So let's go ahead and plug this in. Now, you'll notice throughout this video that I'm going to replace everything and use parentheses when I do it. This is particularly helpful if we have a negative value in here, or when we start to have algebraic functions in there, you're definitely going to want to put parentheses there. If you don't, things like this will definitely become problematic because it's hard to see what is exactly being squared or if like where the negative belongs. So now we're going to follow the order of operations here. We have 8 squared, and that's going to be 64. Now the negative is not included in our parentheses out here, so what we do is parentheses first, we evaluate 8 to the second power, which is 64, and then we will multiply that by the negative. Now we have negative 2 times 8, which is negative 16, and then plus 12. So now we have negative 64, and then we can go ahead and combine these to be negative 4. So that result is going to be negative 68. What that means is that the function f evaluated at 8, the output is negative 68. So another way that we can write the answer is as a coordinate pair where this is our x value and this is our y value. Let's do another example here. If we have another quadratic function here, f of x equals 3x squared plus 2, and we're asked to find f of negative 7, we're going to replace every x in our function with a negative 7. Now, following the order of operations, we need to do negative 7 squared, which is going to be positive 49. Then 3 times 49 is 147 plus 2, so that answer is going to be 149. Now, as I mentioned, it's the function f evaluated at x equals negative 7, and the output is 149. So when we write our answer, we can write it as a coordinate pair like this. Again, where this is our x value and this is our corresponding y value. Okay, now let's address the second thing here. What about when we are given an output and we need to solve for an input? So in the last examples, we were given the x value where we replaced all of these values with the number that we were given. Well, you'll notice here that now we are given the function equal to something. Well, since we have g of x and the value for g of x, what that means is that we can replace g of x, the whole thing, with 6. So once again, since g of x equals 6, we're going to substitute 6 here. So this problem becomes 6 equals, sorry about that, there we go, 6 equals negative x minus 3. And then we follow the rules of inverse operations. Since we have a negative 3 here, we are going to add it. So 6 plus 3 is 9. And then since we have a negative x here, we can just divide by negative 1. So our answer is going to be negative 9 equals x. Okay, so now using the same logic as what we had before, we can go ahead and write this coordinate pair with our x first and our y second. So this is x. This is either the function f evaluated at x or y. Either one is sufficient. Now let's say we're given something like this, where we are asked to evaluate a function. And let's say that our example problem looks like this. We're evaluating the function h at 1. Well, if we're given 3 different functions and our title for the one with h is here, the one that I've outlined in pink, then we're only going to plug in 1 here and here, and then evaluate that function. So really, for this particular problem, this doesn't matter, and neither does this one. So let's go ahead and do that. H of 1 would be negative 3 times 1 plus 1, or negative 3 plus 1, which is negative 2. And that would be our final answer for that, 1, negative 2. Okay. If we were to have another example to evaluate the function g at, let's say, negative 5, what we would be doing is looking at this box here because we have g and g, and we're looking for where x equals 5. So, excuse me, negative 5. So x equals negative 5 right here, and the corresponding y value is 2. So this one doesn't even require work at all. So you might be asking where this will show up. It's definitely going to show up on Algebra 2 quizzes, definitely ACT math, function transformations, graphing functions later, even function compositions. There's a lot of things that you will see this topic on. So hopefully this was helpful for you. I do have a bunch of other topics on Algebra 2, college algebra, and test prep here on my YouTube channel. So you can hop over and subscribe. You can click the buttons below and let me know in the comments if you need any more help.